All right. Good afternoon, everyone, and welcome to today's installment in the Electric Avanar Web News series presented by Emerge Alliance, a trusted RE Plus events partner. Thank you for joining us. This afternoon's webinar is Electrified Transportation, Microgrid EV Charging Infrastructure. There will be a recording available afterwards for viewing on the RE Plus website, re-plus.com. And we will also send a viewing link out via email to everyone who registered. And now it's my pleasure to introduce the co-founder and president of Emerge Alliance, Brian Patterson.
Thank you very much, Trish, and welcome everyone. Today's event is actually a part of a series that we're doing called the Electric Avenue series. It will run for the rest of this year and into 2023. And you can see the schedule here. If you've already signed up for one or more of these webinars, we thank you for that. And you can at any time go back to that registration site and sign up for others if you find the interest in any of the other subjects. After April, we'll probably be adding more webinars throughout the year, and we intend to continue this Electric Avenue series throughout 2023. Today's event is actually going to be on, as Trish said, electrified transportation. We have several panelists as guests today. I'm going to open things up with a brief presentation, and then we'll invite our guests to opine on the subject of electrified transportation from each of their perspectives. What we try to do here is pick three different perspectives, if you will, on the subject, and in addition to our overview from the Emerge perspective and our general membership. One of the things that we recognize immediately about EV charging is the amount of increased requirement that we'll put on the grid, both from a standpoint of overall kilowatt hours needed, as well as peak loads potentials. And that is happening alongside another what we call killer app for electricity. And that's not a negative, that's actually a positive way we hope of describing things, but that's the electric heat pumps. There are other pieces to the puzzle, electric hot water heaters and so on, but those are the big two that are really going to be added on to the grid requirements and generally in buildings. So that's the two we're focused on. When we did the math on EVs, we recognized that the peak, if you actually were to try to charge all the cars and trucks at one time and buses, that it would be about 20 times or so the peak capacity of the current grid. So that obviously is not going to be possible and not going to happen. But if we did look at it more in terms of an average, and that implies that we're going to somehow manage the load and shape it over the days and weeks and months of the year, it still does require a significant amount of more electricity, maybe as much as 40% or so. So there's a couple of things that we think are inherent about getting solutions that will work for all of that, for both the peak and the average loads. One is that the movement to electrified transportation will be gradual enough that we can overcome this kind of massive ramp ups that are going to be necessary for charge points and new capacity. And at the same time, for managing the load, which is really a big part of the solution, you have to put in place a lot more storage and network the systems, particularly at the grid edge. Too many EVs charging at one time at the local level is a huge problem, and maybe we'll hear more about that as we go through the presentations today. So that's kind of the math. We see that the problem and the solution are at the same point, and that is the grid edge, we think. Now, we can add a bunch of capacity at the central point of generation in the current grid, what we would call the grid core. But of course, we have to remember that is not all that easy to do, and at the same time would require additional transmission lines and perhaps expose the grid to more vulnerability to the resiliency issues that plague it to a certain extent now. So we do see that the solution is at the grid edge along with the problem. So where most of that charging is going to take place, of course, is distribution networks of the of the grid included in buildings and so on. So we kind of see the grid edge as both a problem and a solution, if you can wrap your head around that. Now, changing things at the grid edge requires a fair amount of disruption in technology and how the business models will apply and so on. But generally speaking, and it's just an oversimplification, but typically disruption also means opportunity. So there's a lot of opportunity for new businesses, new business models, and growth in the economy of this transformation of energy systems, particularly for transportation. So that's the goodness of it all. Fortunately, coincident with this change in demand and use are a bunch of new technologies that are impacting at the same time. I'm not going to go through all of them, but you can see a list of things that are happening. Some of which you probably heard about, obviously green energy generation and power electronics and storage and so on. Some of which you might not have heard about as much yet, and that is things like transactive harmonic management of the system, or what we call semi-autonomous flow controls, and fault managed digital electricity, along with a whole bunch of new apparatus or equipment that represents the loads, including as we said, the vehicles and heat pumps and stuff, but a continuation of lighting appliances and information communication devices. And last but not least, it gives us an opportunity to really focus on electromagnetic pulse protection, or EMP, solar flares, or man-made disruptions of an EMP nature. So there's a lot of things happening at the same time. In some respects, when we look for a solution, history tells us that we've solved this problem in a similar fashion once for information, and that is the development of the so-called internet. From the time of the invention of the transistor to the time when we had personal computers that were capable of really, as one-offs, create value, took about 30 years. The same evolution from the creation of solar voltaic cells to what we would today call solar systems on homes and such, took a little bit longer. So the energy side has been moving a little bit at a slower pace over the years, and that's a testimony, I think, to the good efforts of all of our grid operators and owners of supplying electricity that we didn't have to think about very much until the last several decades here. But if we look at what happened after that with the grid, it really was that your personal computer wasn't really very valuable until it got hooked up in a network. And then the ability to create information and share it and store it in common places and so on really created a value that, if you're familiar with Metcalfe's law of value stacking in networking, there is going to come a critical mass crossover point where the value of these, in our case, we're talking microgrids or solar battery systems or what have you, the DERs at the edge, are going to be much more cost effective in the overall scheme of things. So, if you've seen one microgrid, you've only just seen one microgrid, and the value hasn't been fully created there. In fact, maybe only fractionally created. So as we look at what happened in the internet to get to the worldwide grid, worldwide internet rather, the internet of not only people and information but things, it took an additional 15 years. So most people would say by 1990 the internet was pretty well established and had made its mark on the operation of networked systems. In the case of electricity, if we move from the time that we first saw, solar and storage systems on homes and buildings around 2015, just 7 years ago, to some of the goals that people have for 2030, 2035, that's only a 15-year period. Using the model, however, that the internet has created and applying it to energy, meaning that we have a mesh network that's bidirectional and essentially, as many people would call it, a virtual power plant concept. We think that there's a good possibility that you can get to a worldwide grid of power with this distributed model fairly quickly. So let's talk about that. And again, internet history shows us that you need two things that really made the internet: new capacity, in that case of computing or information creation, and the ability to store it. So you could buffer and store information. And it's pretty dramatic of what happened with information. And I think there's a potential for a similar future with energy as we innovate the harvesting of energy from more and more green sources, and the use of energy and more effective replacement of fossil fuel use and general use overall. So if we follow that model, it's kind of easy to predict the future, we think, by just keeping an eye on what's already happening and the inevitable, of which, as Charlie Brown would say, everybody's the inevitable going to die someday. But if we take that model of inevitability and apply it to buildings first, and see that buildings will go from passive to electroactive, a lot of BIPV or built-in voltaics and solar voltaics and other harvesting methods go from dumb to smart, and that's all about management of the electricity or articulating it in a way that can shape loads and make things more efficient, to physically isolating it. And this is important to manage against resiliency issues or disruptive issues, whether it's natural or man-made, including EMP. So the ability to physically isolate and yet at the same time continue to operate through different events. And then, of course, as we said, moving from combustion to electric motor, and this could apply to HVAC as well as electric vehicles, although we're showing an EV here as the bigger of the two. But if we put our ability, which is really ahead right now of sharing information, and combine that with the ability to share energy, we will create value that heretofore has been unmatched in our societies and civilization in general. So the not so obvious, maybe inevitable, is that we really need to transition from the centralized kind of unidirectional, albeit trustworthy over the years, almost 100 years of the current grid, to reshape that into a mesh network on both sides of the meter. So we see that even from a utility perspective, there's a recognition that some of that new capacity and load shaping and everything will be done behind the meter, some of it in front of the meter. So a combination of whole system or holonic approach to this control methodology, which also means that we need to focus on multi-directional power flows as well as both AC and DC power flows, because we certainly don't want to compromise or give up anything that we already have in terms of capacity and infrastructure. We want to add to it in the right way. So, and for those doubting Thomases who say, well, it'll never happen on a global basis, it's already starting to happen. Some of you may be familiar with HVDC or high voltage DC transmission. One of the first cables, and I'll call it a green solar electricity cable, runs from Australia to Singapore undersea. That's undersea cabling. So we're seeing the first links. All the other lines on here, which I think I can easily predict are going to be the main routes of electricity transmission from continent to continent or along continent edges and so on, are really where all the internet undersea and cables are. So where there's information, generally there's commerce and work to be done. So that's where we have to get the power there and on a global basis. So that's where we're headed. One last thought about how that all evolves is that we believe that this global grid of grids, and again, we're talking about the long haul now, the 15-year window, that most of the new power capacity will be generated near the loads at the fringe or at the edge of the grid. That it's important that we have the ability to share and reserve electricity and storage capacity that is at the grid edge. That there will be new generation storage and loads that are natively DC current, because we're really in an age now of power electronics and the ability to handle great currents and energy requirements in a semiconductor way, which makes it easier to articulate and interconnect. And that's why we're forecasting that most of this networking capability is going to rely on non-synchronous DC coupling. We're starting to see that right at the individual microgrid level, and I think that's going to work its way up into the grid beyond the low voltage and get into medium voltage, and eventually close the gap between low voltage and high voltage interconnect at the transmission level. By doing the sort of mesh topology approach, again, which is easier to do when it's non-synchronous, so we don't have to worry about synchronizing and phase matching and so on. It means that we'll also be able to have multi-root self-healing kind of self-configuring topologies that will be automatically flow controlled based on both policy and physics. And then that we will, as a result, come to rely more on a very semi-autonomous distributed control. So not necessarily centrally controlled, but a combination of grid edge autonomous flows, flow control, a lot of which will be based on quasi-droop control kind of mentalities and zero risk cyber security administration. And then last but not least, as we are able to articulate our electricity and maybe even create different levels of quality and service characteristics, energy may, in addition to the current, kilowatt hour kind of view of energy as a commodity, we may be able to develop more business models around energy as a service. So we're expecting to see all of that as a result of this transformation as we go along. So today's guests are three, and I'm not sure that all three are here because I know we had, oh no, John is here now. Okay, so we have everybody. And John, if you could open your mic and say hello, I'm gonna let you introduce yourself and talk a little bit about what Agile Fractal Grid is doing.
My mic is open. Can you hear me?
Yes.
Yes. Would you like for me to present from the slides?
Yeah, if you just tell me, I'll advance your slides for you. And
Okay.
again, everybody, this is John Reynolds from our Agile Fractal Grid. And John, if you would go ahead and proceed, we'll get you going.
Sure. I was going to speak to everybody on the electric school bus charging arrangement. This seems to be fairly innocent, but what it does is it ushers in a whole lot of other things relative to the distribution of power just because of this one imperative. So if we could go to the next slide, just by way of a little introduction about the Agile Fractal Grid, for those of you who are not familiar with us, we were actually begun with a project with the Department of Defense. This is a project that Intel was running with them when they had a sole source contract to defend the defense communication network. And we discovered as we got into it that the power grid was a much more vulnerable arrangement. So it got adjusted, and from the activities that went on with the efforts of the military to decentralize the military bases off the power grid, we came up with the concept of this distributed process where you control from the edge as opposed to the central arrangement like Brian was talking about. In this particular arrangement, there's about 4 different tiers that you go through relative to the decentralization, with control coming from the bottom of the picture here, where every fractal, if you will, is able to generate its own power. It has its own very high speed communications apparatus. It has its own computing capability, and it's its own cyber enclave as far as what's going on. But they operate in clusters, so each military base, or in the rest of the world, the college campuses, city districts, other clusters of these arrangements, they put them together so that they operate as a team, so that it makes it more resilient as far as what's going on. At a third level, where you actually have people involved, this is typically a tactical operations center where you're handling problems and dispatching people to the edge. And then you have a strategic mechanism from the top where the watchword is eyes on, hands off. And so this is what we're doing. In order to introduce the speed of deployment, which seems to be required, we have an arrangement going with the Digital Twin Consortium for creating something called the mass customization network that I'll go into a little bit as far as deploying these in very rapid speed in the cadence necessary for the situation we have. Now, the particular picture you have in front of you is an example that I want to talk to you about as far as the planning that's going on up in New York State. The picture here is an actual picture of a live bus charging station over in Japan with one of our partners that we're working with over there. And it uses mega chargers. And the idea here is to buffer all this charging from the rest of the grid so that you don't blow up the transformers so easily within the substations. It also features, in addition to the energy storage necessary for that buffering, a hydrogen-based backup facility so that you can run for weeks without problem with the transportation system if the rest of the grid goes down.
John, can I interrupt just for a second? Are you seeing the whole screen or an edited version?
I'm seeing, I was seeing the whole screen until just now.
Okay, and let me make sure that we got the right screen up there for you.
Yeah, so it's
Is that the whole screen?
It is, yes.
Okay, sorry to interrupt.
That's good. That's good. That's good. So, at any rate, the idea here is this has kind of a traditional value or approach that you're thinking of, but the thing that's a little revolutionary on this is you take into consideration the revenue structure, which actually has nothing to do with the school buses. It has more to do with the services that these nodes can provide back to the rest of the electric grid if you let the utility operate this to their own advantage as far as the local arrangement. So in New York, we're looking at two arrangements. One is working with the New York ISO relative to certain types of services, ancillary services and such that can be offered, but also working with the individual utilities, which are local, because this is the entire state of New York that we're talking about with this arrangement. So let's go to the next slide, if you will. And I'll explain more on this. Just to outline a little bit of the problem with this. New York State is made up of 7 different larger distribution utilities, investor-owned utilities, but it does have 39 smaller municipal utilities and several electric co-ops. So in looking at this situation where you're trying to find out where are there schools, where are there school buses, because this is the law now, all school buses must be electric by 2035. And you need an organized approach to do this as opposed to each utility trying to do this independently by themselves, because it just won't work in time. So let's go to the next slide. I'll explain a little bit further about this. There we go. For the planning process, we're going to be involving all the key stakeholders from not only the state groups, but from industry. And this is not just the utilities, but the various providers that are working on this. And we're going to use a strategy that was worked out most recently in the last decade called the Team of Teams. It was a military process originated by General Stanley McChrystal relative to the situation in Afghanistan, where hopelessly outnumbered by the ragtag group of insurgents, but in this network world we live in, you change the rules as far as how you do things. We're also using an architectural approach used by Eero Saarinen, whom some of you may be familiar with in the architectural world. And the mandate here is never attempt to design a thing without first understanding at least the next greater context in which it must fit. So you have to look at the whole state before you look at any one particular town or charging arrangement, and you need to look at how the state fits in with the region to be able to do that. We're also going to be using Christopher Alexander's adaptation of Einstein's theory of biomimicry, going back to what Brian was saying relative to how the internet came into being. And so this approach lets you simplify greatly what has to be done into what otherwise would be a very complex undertaking. So the planning is going to use these particular visions. And from a modeling and engineering standpoint, we are using the Digital Twin Consortium, composable digital twin. We're going to do this of the entire state of New York with decompositions for the different state infrastructure elements, and then from there decomposed into individual site locations using common patterns. As we do this, though, it's obvious that no two locations will be exactly the same because of the differences of what's going on. But you can do this with the digital twin. I personally am the co-chairman of the Digital Twin Consortium for the global environment for everything regarding energy. Now, as you do this, you have to be using the full digital twin approach as opposed to a piece part tool as far as what this is all about. And so the life cycle approach to this is to engage the digital twin for planning purposes, engineering, the systems integration, construction and commissioning, and the full operations and evolution. It participates in each stage. Let's go to the next slide. Now, this is the diagram that the communications world is now using. This was with our partners Verizon in the United States, NTT globally, Vodafone mostly in Europe, but elsewhere in the world. And so this is the structure that the telecommunications industry is settling down into. It's called the Telco Edge Cloud. And at each level in this hierarchy of the already existing infrastructure that you have in the telecommunications world, you have the opportunity to embed multi-access edge computing. And so each place you see a red dot on this arrangement, you have the ability, if the carrier is cooperating with you, to actually put intelligence relative to what's going to happen. It has little to do with the communication system, but everything to do with the vertical applications like the energy systems we're talking about. And the good thing is, if you use this, it cuts about 2 years off of the process relative to a number of different licensing and other kinds of arrangements. Let's go to the next slide, if we might. With this, from a systems engineering standpoint, we are using a technique called the spine. This, again, is emulating nature as far as what's going on. But we have this pattern of control that occurs at all 5 tiers in that previous slide, in which you have different elements of what's running. It handles the communications, it handles the cybersecurity arrangements, it embeds the different applications in this Kubernetes containerized type of environment. It also allow you to run the digital twin in a decentralized fashion for being able to eavesdrop and monitor what's going on without perturbing the rest of the applications that are running. And we also have a distributed data lake that's part of this, so that the logging and a lot of the volume is actually contained out at the edge. So that's our approach as far as the system side. Let's go to the next slide. And so the challenges were that the regulatory nature of the current utility and telecommunication environment makes this very difficult. I'm sure I'm not saying anything that people don't already know. There are lots of utilities that have to be supported relative to this basic infrastructure if you're going to be doing this on a statewide basis. And the EV charging requirements could, our estimates are it's about double. I know there are different ways you can work the formula, as we just heard, but as far as the raw amount of power necessary, it's going to have to be a lot more than we have now. And a question comes up as to where is the power going to come from if you have to do this by about 2030. Now, the indiscriminate mega charging of the larger vehicles is a real problem relative to the strain that it puts on the current distribution network, unless you have some plan for buffering the power from the charging depots. Let's go to the next slide. Just to talk about the results, this is still in the planning stage. This is obviously a very big project, so we can't tell you exactly what the results are going to be. We can tell you the process that's undergoing with this, but it does allow you to actually meet the timeline relative to what's going on relative to the climate and the environmental imperatives if you use this technique for expanding the way the internet had expanded before. And the model here is being considered for other venues beyond just New York. We have active requests from Colorado. It looks like North Carolina and California are in the queue also. So you'll see this being done slightly differently, but the same general technique for there. The lessons learned for this is that the legislation is required to get it started, but you should not try to justify all these changes on just cost savings alone. The revenue gain is what helps you balance the financial equation. It makes it easier to use, You can use private sector funds when you do this. And the use of the composite digital twin approach is needed to be able to do this at wartime speed as opposed to casual speed. So anyway, that's it. You have my contact information, and that's the project.
And again, there's lots of information on John's slides, and you may want to review that. And all of his slides will be available to you as we go forward. So let's see. Next, we're going to hear from our friend Mike Collum, and he is from NTech Solutions. And Mike, if you would introduce yourself and then get started into your view of things.
All right. Thanks for taking the time to follow this. So Mike Collins, Strategic Account Director at NTech Solutions. We're a division of Faith Technologies Incorporated. If you go to the next slide briefly. FTI has been around about 50 years, electrical construction, a lot of automation. We also do our own manufacturing. So we're truly vertically integrated from concept to manufacturing to installation and commissioning. I think, sorry. So one of the, and this is, I'm learning a lot from the other presenters here too, but certainly the one thing we all have in common is the challenge of adding EV chargers to the grid. And the fact that the edge is really where the action is, it's where the load is, it's where the solution can be. The EV chargers that are being added, whether it's a single level 2 or multiple DC fast chargers, it's a significant new and sustained load. These loads are it's probably the biggest new change to the grid since air conditioning, however many years ago that was, predating probably many of us. But it's a huge impact.
Oops, sorry that when we converted these slides, Mike, some of them didn't convert. You can either, if you have your own presentation, you could use that if you think it would be clearer for folks.
Yeah,
or...
can we do that? Do you mind?
Sure. Let me stop my share and you go ahead and take over the share.
All right.
Sorry, folks, for the interruption.
Let me just find how to do that. There we go. Should be able to see it now.
There you go. Yep.
All right, very good. Yeah, so just real quick. So obviously the challenge is this new load can cause demand charges. It might require building infrastructure or even utility service upgrades. So we work a lot with the end customers, the end clients. And that's really the biggest challenge that they're facing. And certainly it's kind of a chicken and the egg with EV charging. Right now, they may only want one charger. They may only have one vehicle, and they may be able to get away with it for now. But eventually the system is going to have to be upgraded to be able to handle the capacity. The other interesting part about EV energy production is that a lot of people are buying EVs. Companies are switching to EVs for a variety of reasons. In a lot of cases, it's government mandates. In some cases, it's for sustainability reasons. But when you buy an EV, you're basically reducing carbon emissions by, on average, only 50%. So that's a lot, but it's only 50%. If we can start to generate some of that energy with renewables, you can truly have a zero carbon emissions vehicle from charging through operation. So with EV infrastructure, this is what we often talk to our customers about, is what you see is the charger and the vehicle. In this case, it happens to be a truck, but it could be a car. A lot of stuff that goes on behind the scenes, coordination, licensing, permitting, upgrading the gear, civil work. You still have to mount things. You have to have solar array mounting and civil structural for that, permitting, et cetera. And then, of course, the modeling, understand the use case for the vehicle. How often, in the case of, let's say, a fire truck, for example, how often does it run and how quickly does it have to be charged? And so we don't always have the luxury of limiting the charging, but we can certainly help with buffering if the charging must be full power. So our process, we go through a 6-step process, and this is what we do, whether it's an EV charger application or a microgrid distributed energy system. We always start with an assessment. Get the electric bill, get interval data if at all possible, metering data if they have it. In some cases, we'll actually install metering to better understand it. Engineer the system. Now we take the model, we size the equipment, we figure out what kind of distribution upgrades might be needed. In the case of EV infrastructure, when you're going to a commercial building that's adding a charger, such as a fire department, oftentimes they only have 12208 volt 3-phase and maybe only 400 amps, when in fact you need to add a 480 volt DC fast charger, which at 12208 would be another 400 amps. And so a lot of times you've got to be looking at a utility upgrade or distributed energy resources to keep the system completely off that grid. Sourcing, we do our own manufacturing, as I mentioned, so we can either source our own or others. Then, of course, the installation, making sure that things are where they're supposed to be, operating the system, and then optimizing it by using the data from the charger management software and or the microgrid energy management system, so we can understand the power flow, we can understand the demand charges, and we can help to mitigate those with the controls. This is just an example of a graph that we use. So Energy DNA is our tool that we use to model a system at the beginning. And so not only do we look at the utility data, as I mentioned a couple of slides ago, but we also then overlay that with solar power that we can either put ground mounted or rooftop, especially when we're doing a completely off-grid system, which I'll show a couple of examples in a moment. It's important to really understand how much solar we can produce. In the Midwest, it's very iffy when you talk about December, January, February. And so we've got to have backup plans for when we don't have enough solar to cover that. Microgrid, I'm sure you're all familiar with this, but essentially the elements of a microgrid, visually, our fundamental energy generation is typically solar. We do wind, but solar is probably more prevalent. We have our own control systems that we have developed with battery energy storage, sizes down to 20 kilowatts all the way on up to a megawatt. And then these systems then can either be grid tied or they can be completely off grid. So the basis for our off-grid EV chargers is the smaller system. And this is an example of one that we did for a car dealership. A lot of traction for this particular application. We've done quite a few of these now. This particular system is at a Ford dealership in Neenah, Wisconsin. And the challenge was that ended up putting in one DC fast charger at one dealership. And the owner was shocked at the demand charges that he was seeing when he first started using that charger. So we brought the solution that said, let's try this completely off-grid system. Let's demonstrate the ability to charge without utility. And so we put in two basically parallel systems, one in the service bay and one in the customer lot. Each one has a large level 2 charger. I think it's 16.8 kW. And the system itself is 18 kW. So we can charge in 1 year, we can charge between those two systems about 1,000 times. Now that's a 50 kilowatt hour charge. We were doing this for the Mach-E. When the Mach-E was introduced, we needed to be able to be prepared for that. And so that was the reason that we did this at this time at this dealership. And you can see the overhead about how much space it takes up. And again, that's two systems. You got about 1,200 square feet of solar to do one level 2 charger for one vehicle. And again, half of the goal was also carbon reduction, the additional carbon reduction versus charging from the grid. I didn't mention, you can see it in the corner here, we do have a natural gas generator. Again, I mentioned Wisconsin, December, January, February, not a lot of sun. So we do rely on that in those months to help to make sure that the batteries are charged, but we tend to use the batteries as much as we can. Another charging example that we did was at Road America. It's a race course in central Wisconsin. We actually put a charger there, but we actually tied to the grid. We rooftop mounted the solar and we connected the system to the grid because they're not charging all the time. They're only really charging customer cars when they're there, which is only some days per week and only some weeks per month, summertime only. And so the rest of the time we're harvesting that additional solar to be able to be used behind the meter for their track. Again, same kind of design as the other one. The good thing about, or the cool thing about these systems is they're rapidly deployable. We can put a complete system in to do these chargers in about a week with 3 guys. Now, lastly, this one is not renewables, but it indicates the challenge that we're going to be facing as municipalities start to expand to electric fleets. So the bus example, we're starting to see some of those as well. Buses, delivery trucks, and they have to come up with charging. And right now, for the one fire truck, it takes a 150 kW DC fast charger, and that's still going to charge the vehicle in about an hour to an hour and a half. So it's still a substantial amount of time on a fast charger, especially if it's got to turn around and go back out again. As I mentioned, many fire stations only have lower 3-phase voltage. And so we either have to do a step-up transformer or sometimes bring in a new feed. We're also investigating the buffering concept, as the previous speaker actually talked about, that we've got some of those in application as well. Our smaller systems really use the battery right now for that, even though it's a lot smaller. But we definitely see the need for doing buffering as we go forward with some of these larger applications. So back to you, Brian.
Okay, thank you, Mike. And we had a couple of questions come in, but I think we're going to wait until the end here after Gary presents. And let me just advance my slides up here to get caught up with Gary's presentation. And Gary, maybe in the meantime, you could introduce yourself.
Yeah, Gary Opedal with Amera Technologies. Our product is Block Energy, and I will start with an announcement. We have our first big commercial operation outside of the military in Tampa, Florida. And while Hurricane Ian knocked out power all around us, our microgrid, our renewable resilient microgrid, weathered the storm all the way through it and still is up and operating all the way through. That's a big deal. Part of what we're trying to talk about here is energy systems versus power systems. As Brian said earlier, non-synchronous, normally off systems that we can put at the grid edge and make a new grid from the grid edge inward. And this was the first big test. This is owned by Tampa Electric. It's 37 Lennar homes south of Tampa, and it's a big deal that worked. We're extremely happy about that, and that's what we see as the future. But really, all of our customer needs are changing, and how can we keep up? As Brian likes to say, you know, it's easy to predict the future. Just keep a keen eye on the inevitable. But I also like to add to that is, it's one thing to have a goal. It's quite a different thing to have a plan. And we all saw that California, you know, Brian said that this would be a gradual implementation. Well, maybe, but gradual like smartphones, which none of us had, you know, just 10 years ago, and now everybody carries one around. If you look at California, who just a couple of weeks ago said no more ICE internal combustion engine car sales by 2035, and then 12 states jumped right on that with the next 2 weeks. So I think it's going to come faster than we think. And remember, fast to the utility world is a big deal because they're used to glacial speeds, right? And so it's going to feel a lot faster. And this slide talks about the increasing uncertain challenges. Can we decarbonize? Can we go through the transition to electric vehicles and keep all the lights on? So next slide. I think that, you know, we do say on the average, we're going to have these EVs all over the place, but quite frankly, they're going to be concentrated in big cities and other areas of wealth as we electrify everything. And then the time of charge, if you've got two people commuting with EVs in San Francisco, they're not going to want to wait until 5 in the morning to start their charging. So we're a big believer in distributed storage, and I'll talk about that here in a minute. But the major challenges that utilities face, and indeed the entire grid face, is that residential EV growth demand. We all talk about EVs are going to drive the market with respect to DC, asynchronous power, and electrification needs at the home, pun intended. And EVs can add 1/3 to 50% of the load of a house, and let alone multiple EVs. And the fact of the matter is that there's no neighborhoods in America today that can handle 1 EV per home, let alone 2. And so how are we going to do that? The transformers were never built for those kinds of loads at that edge, and they're not built for backwards flow of energy either. So that's why we think that distributed storage is going to be a big deal, and I'll get to that in a minute. But sustainability, they're under pressures for sustainability and energy transition, energy equity, resilience concerns, and we just answered that with our demonstration in Tampa with Hurricane Ian. But we are going to see more and more weather events with Uri, and then as states electrify and renewable more and more and more, there's going to be pressures on the grid. Some people would say that for every megawatt of renewable energy, you've got to have a megawatt of thermal energy for when the sun doesn't shine or the wind doesn't blow. Well, we would say if you've got storage at the neighborhood level, then you can implement renewables quicker, but that's not what's being done now. So we believe that the overall grid is going to have concerns for decades to come. So next slide. The major challenges that utilities face are really exacerbated by the fact that this is difficult to solve because the aging infrastructure can't meet new demands. Try to order a transformer right now, and so as we start thinking about how we're going to retrofit current neighborhoods and how to build new ones, we're in a real trouble. And there's lots of different solutions. Now, we believe that, and we want to partner, the two folks as presenters today I see them as, co-opetition and partners, worst case, because it's going to take all of us to get together and do this to solve the problem. And we all have to be interoperable. We all have to work together. Next slide, Brian. So I won't spend a lot of time on this, but there's operational complications at grid edge with interoperability and many different designs. We've got business revenue erosion as people put their own stuff behind the meter, and then there's shareholder pressure on utilities. So utilities are going to be hard pressed to move this forward. So what are we going to do? So go ahead, Brian. This is going to say, is there a solution? Yes, there is. So go ahead. And this is just go ahead and click again. You'll see this is drone footage while we were under construction. This is in Tampa. All of the houses you see around this across the lake, etc., lost power during Hurricane Ian. This neighborhood, which is now complete, I'm showing this drone footage during construction, stayed on. You'll notice integrated solar into the roof, block boxes next to each and every home provide storage by every home, and they're all hooked together. So all the solar is shared, all the storage is shared in this community. So you don't have to worry about not having enough on your home. So the Thanksgiving thing, you can use the rule of aggregation. Thanksgiving, everybody's at one house, nobody's at another, everybody just shares. And that's the cool part about a microgrid. So it doesn't matter if one of these houses had no solar on the roof, the system would still work. Next slide. And this is all backed by Amera. Amera is a $34 billion energy company that owns assets and utilities. But they asked us to take a blank sheet of paper and figure out how to get utilities and anyone who's interested in microgrids moving forward. And that's one of the secrets to what we do. So next slide, I want to get to EVs here. So if you look at a line diagram, and as Brian was talking about modular and John was talking about buffer, and Mike said the same thing. What we're saying is, look, there's three places you're going to charge your car. Now let's not talk about fleet. Mike talked about fleet a little bit. John did too with buses. I'm talking about individual cars, which all of us are going to have by 2035 if the government's wish comes true. So we're going to either charge them at home, we're going to charge them at work, or we're going to charge them on the road. So we think that a large part of the charging is going to be done at home, although we have solutions for on the road and for work also. But if you're going to do that, then distributed storage in the neighborhood is like a buffer. I'm an old Intel guy. You know, you want to set things up so that they're modular. And in this situation, you're looking at a outset of a single home off to the left. If it's part of a microgrid that's more powerful, it can share energy, just like an individual PC would share energy in a local area network. That's more powerful if you have a central server, which is what we call our block central. That's more powerful if you're hooked to the cloud, which we stay hooked to the utility, because the utility we can take from the utility if it's cheaper for some reason, or we can supply voltage bar support, reactive power support back to the utility as it needs, or energy. And so we think that that modular way to do things is the way to go. But the other key component of this is every single block box next to every single home has a bunch of storage in it. And that's DC storage. So you can take in energy from whatever source, whether it's the grid, solar, geothermal, wind, doesn't matter. And you can store it and then go from DC to a DC car. Why would you make that last DC to AC to DC conversion for cars and then everything else that we see that's going to be DC in your home? So next slide, Brian. And then you just stack these up as we go into a grid of microgrids, all connected to the cloud, so to speak, the utility grid, but then connected to each other in about 50 home blocks as we go. So next slide. We have this in some small C&I and military, but you'll see here that our concentration is on military and working with EV chargers, both AC chargers and DC to DC fast chargers and other technologies as we move forward. In this case, the military. Next slide is our first implementation in Florida, as we said, and this is in rate base owned by the utility, by the way. And then the next, go ahead, next slide. Let me just flip through these, Brian. I don't want to. Now this one is key. This is a block box. Now this is the power plant for this home. This is a digital transformer or a solid state transformer. So instead of the green boxes that you see every other house, this is what next to the house. It's no bigger than an air conditioning coil, but it has all the storage, all the power electronics, and all the controls to power that house, grid or no grid. And that's what's taken us through this last hurricane. And that's what's the beauty of this. We believe in a mesh network of nodes, which takes a distributed, modular, normally off, non-synchronous approach. And then that local buffer then can power that house and charge EVs. Next slide. And I'm almost done here. This is one of my favorite ones because it's up in Maryland and it's affordable housing, a segment of the population that we've been leaving behind. But these houses are passive homes. They've got a block box next to each other. So they have the renewables, they have the resilience. This is working with community solar because this is a deregulated state in Maryland with Pepco and Exelon, and they can have EV chargers. And that's all included for these folks who are affordable housing. And our central energy park is in that home, quote unquote, at the bottom there, hidden by a home-like structure. This is just a user interface that shows the energy. You get second by second, watt by watt data on this, as opposed to waiting for a phone call that something's wrong with your grid. Next slide. And I think I'm almost done here, Brian. Just mentioning cyber. We can use an optimization, control, and safe mode, which uses some of that voltage, the droop techniques that Brian talked about, to make sure that we're thinking about, as we put in smart inverters and smart distribution systems, we're putting in cyber as we go. And we're working with San Diego National Labs on that. So next step is to just, talk to us about how does this all fit together? Is it John's system? Is it Mike's system? Is it our system? Combination of same. How do we get to the future with a grid edge grid of grids solution that's all interoperable. Because again, it's one thing to have a goal, it's quite another to have a plan. What's the plan to get to where we need to go?
So in the last few minutes, I'd like to answer some of the questions that have been coming in, and I'll try to take them in order. From Janelle Cruz was a question about customer cost savings in projects where EV chargers are powered with islanded microgrids instead of the utility. Are there, and I think that was aimed, well, it can be aimed at anybody, but does anybody wish to answer Janelle on that? What are the cost savings projections for EV chargers that are powered with islanded microgrids instead of from the utility? And if
I would just say that you're going to have power when the grid is out. And that's the last thing you don't want to have is no power and no transportation. The cost savings are, as everybody else's rates go up, as we try to do more centralized solar and centralized storage, our rates, we put this into the Florida market at current rates. So the people across the lake who did not have power during Hurricane or Ian, our folks are paying the same rates, but they can charge their EVs and they can live in their house.
so the model that a lot of people refer to is when hurricanes have come through and you lose gasoline station power, then people, even with gas vehicles, gasoline vehicles or diesel, aren't able to get fuel. And they lost the use of their vehicles, which panicked a lot of people. I remember when Gloria came through up in New York area and other hurricanes. And I'm sure Florida is in that situation now where many of the service stations that you normally get gasoline, and even not only for your vehicle, but a lot of people had gasoline charge or generators that couldn't get fuel either. So the idea is to have the fuel, and certainly the microgrid, an islanded microgrid, can supply a reasonable amount of fuel as a priority to your vehicle if that becomes the priority there. So
Right, and homeowners haven't paid a dime for all that kit, so they're not paying anything for all that. Neither is the home builder. The utility is putting this in instead of status quo, and we're utilizing the current AC system. I think it's really important. I think somebody made this point in the Q&A, and that is, don't scrap what you've got, work with it. And so we're putting less pressure on the AC current grid. We can add to it as an asset with energy, voltage, VAR support, reactive power support if it desires. But if the grid goes out, we stay up. And so this is the whole, it's nobody wins unless everybody wins, right? So let's work on systems where everybody wins.
Okay, I'm gonna apologize to everyone. It's 3 o'clock here in the East Coast time, and whatever time it is in your zone, and we're technically run out of time. But I'm gonna leave the webinar open to answer some more questions, if it's all right with the panelists. And anybody who wants to stick, we're gonna keep going down the questions and see how far we get. So if you have to leave, thank you for coming, but we're going to continue on. A general set of questions is about controls. The current controls, by and large, with electrical systems are based on conventional SCADA based EMS, and there's apparently a need and a recognized need for a much faster acting system and more distributed capability. Anyone want to comment on controls? And I think this applies to all 3 presentations, so anybody can take a shot on controls.
Our system interfaces with SCADA easily. In our system in Metro, the neighborhood is controlled by the utility. We feed all of our alarms, information, and everything, and whether they are, whichever way we're moving electricity around is controlled through the SCADA system. So we interface perfectly with it.
But if I'm not mistaken, Gary, in your system, that block box, or what you call the block box, has a distributed control. So if it gets islanded, it continues to operate on a distributed control methodology, right?
That's right. And exactly as you said at the start of this, Brian, we've got to have, if you're going to have distributed resources, distributed solar, distributed storage, well, then you need distributed control, and distributed control is much easier. You don't have a central control system that is a single point of failure if it takes out, if it gets taken out. And so you need distributed controls anyway, and that just makes that mesh network of nodes that operates regardless of which things remain in the system. And when you add new things, it just says, hey, I'm on the system and interfaces with everybody else. So there's no need for central control changes.
Yeah, so the conversation with the SCADA control or central control at a utility, whether you're behind the meter or in front of the meter, it might be there, but it's not at the individual microgrid operational level. It's more in the coordination of demand response and grid support, frequency support, all the bidirectional elements that are available from the microgrid network.
Yep.
Okay, the question was about how about retrofitting buildings and especially where there's limited or not ideal roof orientations and limited ability to apply solar. We've kind of talked mostly about solar here, but I guess we really are remiss not to say that it really applies to any means of local power generation. You heard a little bit. Mike talked a little bit about natural gas generation. There's also a big and coming technology and increasingly useful technology is a hydrogen fuel cell. So really it all applies whenever we use the term solar, we really mean green generation of some sort. So you might not have any solar, but if you have hydrogen fuel cell, or if you have wind turbine, or you have even natural gas with a carbon sequestered emission control. We've seen now generation off of natural gas, which vents to the interior of the building. You know, it's so clean. So I think the technologies that can be applied in the distributed generation field to handle those applications where solar spatial area is not available. And of course, this even more importantly applies to urban settings where you have multi high-rise buildings and so on, which just do not have the footprint available, even including built-in PV with glass facades and so on and so forth. We're going to see more innovation with solar, so there'd be more harvesting there, but I don't think anybody is saying that that this so-called grid of grids or networking is dependent upon solar exclusively. Is that
No,
anybody want to comment there?
Yeah, no, as a matter of fact, you don't need solar on any given roof in a microgrid because it can all be shared between roofs, or you can have some carport for EV fueling station solar, or you can have other generation or even the grid. You're going to have buffers in the neighborhood for EVs, et cetera. Where the solar goes is a whole nother story. Like I said, in Maryland, we're using community solar because it's a deregulated state. You can't own D and G. Now microgrids weren't contemplated when we did deregulation on behalf of consumers. So we did a community solar program, and then that community solar comes into this microgrid. That it can be offsite, it can come from anywhere. In high-rise situations, we're still going to have some utility solar. Again, it's and not or.
So a question that goes along with that is that many, if not most, and this comes from Fernando, many or most utilities forbid charging batteries from the grid. But that's likely to change, is it not? If especially whether it's behind or in front of the meter, utilizing batteries wherever they are, or storage wherever it is probably going to be important to this whole concept of grid of grids, right?
I want somebody else, Mike or John, to pipe in here, but I listen, we're going to have storage. And so think of it as video buffering, which is why we can, live stream things these days. And remember how clunky it was when we were first trying to do this. We're going to have buffering at the neighborhood level in whatever form that takes. And so we're going to have to be able to charge batteries from various sources, or it's not going to work. The current system just won't work. So we'll have to work on all of those.
Yeah, agree with you, Gary. The batteries for buffering, so renewables are only good until they're not there. And so if the more renewables that get put in, you've got to back that up with battery energy storage. You can also use it to, peak shave. You can use it to time shift, obviously. Use it, store it when rates are cheap, discharge it when rates are expensive. I mean, there's batteries are going to be key, and as the prices come down, the capacities go up, they're going to be an integral part of the edge power distribution.
Certainly, as was the case in information storage, we really want to get to the point where we have a squanderable supply of storage capacity. It's just like the thumb drives I have sitting in my desk drawer here. I probably have multi-gigabytes of storage that's totally unused, but really convenient when I need it, right? So we're going to see the same thing there. And people ask, where should the storage be? And my answer has always been everywhere. In other words, wherever storage makes sense. You might even have storage integrated into individual appliances and devices at some point. We don't know, but whether it's at the individual enterprise or at the block level, on the street, or in the neighborhood level, et cetera, we're probably going to see storage in each layer. Some of it fast acting, some of it long duration, flow batteries versus lithium ion, and so on and so forth. So I think we're going to the buffering capability and storage capability to take electricity and out of the immediately dispatchable category is key to this whole scheme working. So another question.
I always smile, Brian, when people are surprised when their solar doesn't work when the grid is out. Unless you have a storage and inverter on your house, your solar is illegal. If the grid goes out, you're out also. And so unless you have storage at your house, you're not even going to go through a grid outage. It doesn't matter how much solar you have on your roof. So your answer of everywhere is very germane, because when California was going through their PSPSs, it's every summer now, but initially a few summers ago, and people were shocked that the solar that the state required them to put on their roof doesn't work when the grid is out. It just we need to have more and more storage everywhere. It doesn't have to be lithium, but it has
it was painful to watch both in New York City, but more importantly in New Orleans when Katrina hit, and you just saw these flyovers where there's solar on a lot of roofs, including a lot of municipal stadiums and storage facilities and so on, had solar on the roof, and it was totally unusable because it was not tied into storage or any way to isolate it from the grid. So that's going to be important.
That's very, very misunderstood. Most, probably 90% don't understand that.
And we also shouldn't underestimate the ability of hydrogen eventually to be sort of a form of storage. Hydrogen is so dense from an energy standpoint, and providing we have ways to convert to and from the nascent hydrogen, which looks like fuel cells and PEM cells. I think that hydrogen is going to play a major role, not only in sort of providing a capability of additional source, but also in storage. I want to answer another question, though. People come up and say, with home charging, and we've heard this too. I heard recently a person who had a Hummer complain that it would take, when he plugged it into his level 1 charger, it estimated it would take 4 days to get a full charge in his Hummer. Of course, we know that a Hummer probably has a healthy appetite for battery and so on. But even when level 2 charging was applied, it still was more than 24 hours of charging to get from around 5% to 80%. So this whole idea is there a possibility for faster residential charging with DC, and where does that sit? And before I throw it open to the rest of you, I do want to mention that we just held a live demonstration at RE Plus in Anaheim, the trade show, where we demonstrated a faster charging DC charger at home. And essentially what it was doing is combining the utility power live, if you want to consider it a dispatchable source, and then combining it with the storage source that was at the home, and actually boosting it up from typically what would be a 10 to 20K system up to a 30 to 40K system. So you get 30 or 40% faster charging than the 1 day charging. Because I do believe that people are going to be hard pressed to fall in love with 24 or 48 hour charging. We're a society that likes to do things quickly and not have to worry about things for more than a few minutes. So, to get charging at home, at least under that couple of hour window is important. You want to comment on that, both of you, Mike and Gary? By the way, John had to leave, so he apologized. He had another engagement, but please
Yeah,
go ahead.
I just
Mike.
have 2 minutes myself too. So I can address that too. So first of all, continually rapid charging a car is not recommended. It's not great for the batteries. When you're traveling, it's great, but using a fast charger every time is not recommended by the manufacturers. That said, there are DC fast chargers today. There's one that we looked at that's 24 kW, I think, and it's a single phase charger that you can get, DC fast charger. You can also get leverage the battery energy storage that we talked about. Buffer it depending on how often they actually have to charge it. If you have to charge it every night, that may become a challenge. But if you have a day to charge the batteries and then do a rapid discharge, very similar concept to what we're looking at for fleet vehicles, but just on a smaller scale for residential. That's a solution that's available today.
Yeah.
Mike's right on with that. It does damage. There's three things that kill a battery, right? One is the speed of charge and speed of discharge. And then the second is temperature while you're doing that. And the third is how close to zero and how close to 100% you get a charge,
right,
depending on the chemistry. So the faster you charge, the more you're taking life away. Now we can argue about it, so what if it decreases my battery by 6 months over 15 years of owning a car. I don't care. And quite frankly, as a lead-footed Tesla driver, I can tell you that I don't care. But it does matter in the long run. The thing I want to address though is this thinking that of the average. Well, the average commute is only 12 miles, each way, and so everybody can charge their cars between 5 and 7 in the morning, and we won't have to worry about peak. Well, I'm here to tell you, as an EV driver, that doesn't work for me. There's times when I have to travel to Santa Fe to testify before the legislature tomorrow morning, and I need to start now for my level 2 charger to be full charge to get there and back tomorrow in the morning. And so, and this is going to be a city problem first, with 2 commuters per household. And I don't think we're going to be. It's part of the answer. It's not the full answer to say that we're just going to control when people charge their cars. I think it's part of the answer. It's not the full answer. We're going to have capability and capacity at the neighborhood level, in my humble opinion.
Okay, so one of the other questions that comes up is about this idea of neighborhood sharing power, really. First of all, is the deployment of the system, is it going to have to be all at once, or can it be incremental? Particularly, of course, with new builds in a new neighborhood, you can do it all at once. But what about existing neighborhoods? Are we eventually going to be able to kind of take sections and start to populate it? And I kind of look at the model, and I always look at the information system and how that was deployed. That whether it's a utility or a third party or the owner itself, it's like, how can you deploy it one at a time and then connect it all together eventually? Whether it's like the cable systems connect internet all together, they sometimes go into a neighborhood and cable it up at the curb, but not necessarily connect every house until the house subscribes and so on. So what kind of business models do you see there, both of you?
Well, I mean, I see it has to be incremental. We're not going to replace the whole grid tomorrow. That grid's been around for 120 years. It's the world's largest machine. I will say that the UN has stated that 80% of total energy use in the world is going to be electrical by the year 2050. The DOE came back and said, let's look at that study, and they've come up with 60%. But let's use the lower number. Right now, current electrical energy use versus total energy use, think about combustion engines and diesel and gas and oil and everything, is 19%. So everybody on this call needs to be concerned that we have to triple the current grid as far as capacity goes. Now, all that doesn't come at once, and just like your example with EVs, we don't charge them all at once, but we're going to have to get going if we're going to electrify everything, if that's our answer. If it's not our answer, that's fine, but everybody says that's our answer. So if you say that, we have to be consistent with our planning to get there, I think. And so toward that end, we're going to have to be able to build this incrementally at grid edge, and then kind of support the current grid with taking pressure off it by grid edge, and then going into retrofit when that makes sense. And that will make sense once we can't just depend on new neighborhoods to get to our renewable portfolio standard goals state by state by state. So eventually we'll come in and we'll have to start figuring out how to retrofit, and it'll make sense from a cost wise. The only reason why we're not retrofitting now is it doesn't pencil. It pencils for new neighborhoods because you don't have the stranded asset of your current AC system. You put this in instead. Every new technology goes through that. First, it's a choice. Do you do this or this for a new purchase? Then it is, okay, when I replace my system and it gets old, what do I do? Okay, I do this. And then it is, when do I retrofit? That's every technology. And we're on that curve right now. Right now, it makes sense for new. Eventually, it'll make sense for retrofit.
Yeah, another interesting question is about the perspective of wire capability and the current AC wiring and transformer transmission infrastructure versus, what the internet did was kind of change that paradigm fairly significantly from AT&T copper wire kind of transmission over to, fiber optics and wireless and a variety of different means of communicating. What do we see, or does anybody start to see? Before I say what we've seen from an eMERGE perspective, are you seeing any attempts at changing the AC wiring, either retrofitting it? And as I always say, the electrons themselves don't know if they're AC or DC. They both can travel through copper wire, for example, and actually at equivalent voltages, there's better transmission properties with DC than there is with AC. But how far is that going to go? Can we actually retrofit without tearing out all the wiring we have?
That's the good news. Your wiring in your house right now doesn't care, like you said, if it's DC or AC. And so, as we showed at the show with our new, and Brian alluded to it at the RE Plus show, we had a DC refrigerator, a DC washer, a DC dryer, a DC robotic vacuum, a DC train unit doing heat pump air conditioning at the show that was on and running, DC fast charger. As we do more and more, in 20 years, you won't have an AC panel circuit breaker in a home. It'll all be DC because all those things are DC now. It's all DC motors. It's just we convert from AC to DC because AC is what we've got. But eventually we won't do AC anymore. It'll all be DC. What's the transition? Who knows? But I would say that more and more we're going to say, let's not generate in DC, store in DC, convert to AC to power DC loads. It doesn't make any sense. Why waste the conversion of that last bit? And the good news is the wires in your home will handle it. What they won't handle, at least as far as I know, is technology. Brian, maybe you have seen something different, is DC and AC over the same wires at the same time. I know there's some technologies that are working on that, but you'll have to make a transition at some point on parts of your circuits at least.
Yeah. So we're already seeing people come up with kind of retrofit kits where they would slowly convert as something obsoleted out or broke down in your house, like a heat pump or an air conditioner or a washing machine or whatever, that you would replace it with either an appliance that could take either AC or DC, because that's a minor change in the appliance itself, since most appliances natively are DC now inside with brushless DC motors and electronic drives and so on, variable speed AC motor drives, which are all DC electronically driven. That it would just be a sense of moving the connection from an AC breaker to a DC breaker and so on. Now, are there standards for that yet? No, but that's what we're working on. We're trying to get to that level. And are the appliance people making units that can take both AC and DC? Curiously, they are, but only by default, in a sense that most appliances, even though it's converting AC to DC inside, could take in DC without very much of a change. it would be better if we did that in a standardized way. So we are working on standards that suggest that appliance manufacturers start selling goods that can either take AC or DC without modification. So it's a matter of, even if you bought an AC refrigerator and later on put in a microgrid or a solar storage system that was capable of delivering DC, that you would just have the electrician switch the wires over on that device, and you wouldn't have to throw out your brand new or reasonably new washing machine or refrigerator, what have you. So we are working on solutions that provide for that soft landing, if you will, of conversion from AC to DC. But that's really important. Question came up about regulatory barriers from one of my good friends and consorts, Larissa Dobriansky, who's working on this within the CEPA organization. But there are significant regulatory barriers on getting to these business models that we talk about and to community microgrids and so on. And we could probably have, and we will in the series, have a separate discussion about regulatory changes and regulatory barriers and so on. So with all due respect, Larissa, I'm going to defer that to a future one. In fact, and we'll have you speak because Larissa is an expert in this area, and the CEPA organization, the Smart Electric Power Alliance, is working in this area of paradigm change from a regulatory perspective. So we'll want to get them to opine on that. The one thing I wanted to mention just real quickly about the wiring is one of the ways that we can get current carrying capacity up in wiring is to raise voltages. And of course, but that suggests potential safety issues or whatever. But there's a pretty significant effort right now headed by a good group of companies, including Cisco and Eaton and others, who are working on what's called fault managed power. And it's essentially taking DC power and allowing it to have the equivalent of zero crossing or fast acting fault switching, which means that instead of having an AC, we typically do our fault management at the zero crossing points of the voltage. That you can actually get an equivalent but much faster acting safety capability with DC electronically by creating those same interruption points. And if that happens, then it's likely we're going to see even higher voltages than we're currently seeing. And remember that when voltage is talked about, we're seeing the root mean square result of a voltage. In AC, for example, the 240 that your house normally takes in is really about 336 or something like that. So it's up in the low 300s. So you're having to deal with a higher voltage from a safety standpoint, but you're only going to get the current carrying capacity of the 240 volts because it's a root mean square average, right? Area under the curve. With DC, you get the whole thing. You get everything under the curve. So if we went to something in the mid 300 range of voltage, the safety implications would be the same. It would be better at fast acting, and the switches that I've seen are now operating at 600 to 1,000 hertz. So 10 to 20 times faster than the zero crossing in AC. So fault detection and action is so fast that you could grab high voltage wires with your bare hand and not get shocked. It just simply shuts down the system too fast for you to get a shock. So we're likely to see that. So you're going to see, in many cases, raising that voltage, which means using the same wire, if you're using 12 or 10 gauge or 14 gauge wiring in your home, that you'll probably get 30 or 40% more power through the same wires. So that's a solution. I just wanted to point out that that's happening as well. I think actually we've run out of time, but what I want to do, we're a half hour over. So I'm going to take the rest of the questions, and I really thank everybody who was kind enough to ask questions. We're going to save those questions, and I'm going to circulate these questions out to everybody, and they can answer them at their convenience. And I will attempt to answer as many as we can. Please come and visit us next week if you have time. We're going to be in Florida at the Doubletree Hilton Convention Center in Miami. talking about the grid of grids, and that event is held by RE+. Some of you know it as SPI, or Solar Power International Energy Storage, and so on. But we will be there doing presentations, and we'll also be online with additional webinars, as I mentioned before, that you can download at any time. Let me go back to that kind of schedule here if I can. Can you see that? So we have lots of webinars coming up, and when we get to April and beyond, we're going to be scheduling some additional webinars in this same stream of consciousness. They're all free, so we hope that you take advantage of that. And for all of those who didn't make it today, these webinars are going to be online, both at the RE+ site and the eMERGE site. So you can free download them, and please use them to talk to your associates and customers and other people about preparing for the future. But again, you didn't see anything here today that requires an invention. All the technology is there. It really is more about organizing the technical acumen and capability that we have in the right direction, and we can certainly get to a solution that can be fairly rapid, as Gary mentioned. Just a footnote on all this: it only took 11 years to go from horse and buggy. About 5% of the transportation was horse and buggy, to get to 80% combustion engine vehicles. It took about 11 years to do that. And one of the important concepts that I try to remind people of, while it required new vehicles, so to speak, or new machines to do that, they rode on the same roads. And the advantage we have with electricity is we can use most, if not all, of the existing wiring that's out there and make this transition without having to rip everything apart and start over again. So we definitely want to combine what we have with what is possible for the future, and move as quickly as possible, and get to this new paradigm of a new age of electricity, really based on power electronics and extreme resiliency. So thanks again for attending and staying with us. And like I said, you're welcome to download these from online when they'll be on one of these sites here. You can click on these QR codes. I'll leave this up for a while, and go to either the eMERGE site or the RE+ site. And eventually you'll, if you're registered for this, you'll get a notice of when those recordings are available. So thanks again. Have a great day. Thanks to our speakers, Gary, Mike, great job. And we'll see you soon. Thanks.
Thank you.